Welcome back again. We have just now recognized from the E naught value how to identify an oxidizing and reducing agents. Now we are trying to apply them and try to see whether a particular reaction is possible or not. Again, what I will do is I will go back to that zinc and copper sulfate reaction, that galvanic cell. Now I am giving you the E naught values for both the half reactions here. That is, I am writing like this, try to follow the E naught for zinc plus 2 zinc. The way it is written, I think it's obvious for you. What I'm writing first is a reactant, and what I'm writing later on is a product. And if this value is negative, so where are we focusing on? Zinc as the reactant. The product is the main thing for us. The product is the main thing for us. Now this value I'll write in the next time. Now similarly, what is the other half of the reaction? That is E naught, copper plus 2 copper. Again watch out how I am writing here. Is it looking like a reduction reaction? Copper plus 2 must accept electron to form copper. Zinc plus 2 accept electron, therefore reduction to form this. This also has E naught value. And I am giving both the numerical values now. Please copy that. For zinc plus 2, the reduction potential value is, this I am taking from one of the standard textbooks of electrochemistry, and that value right now is minus 0.76. This value minus 0.76 volts. Minus 0.76 volts. Negative value. Please bear that in mind. What is the other thing? Please, copper plus 2 copper. That particular value is copper plus 2 copper is copper plus 2 copper. Where is that value? I think it is 0.36, 0.3, some positive value. E naught value is, imagine, I am unable to get that value, we will take the approximate value, 0.34 volts, approximately. Positive value if I don't write anything there. Now these are the E naught values. So what is the meaning of that? How do you interpret that value? How do I write the reaction from this place, which is taking place spontaneously? I'll pick up this because this is supplying electrons. Remember, negative elements, I must focus on this. So how do I generate a reaction? Zinc, reducing agent. And what is my oxidizing agent? Reactant here. Therefore, electrons are moving from this to this. That is, already we have talked about this example, therefore you should not struggle. But using this information, you must be able to predict whether we can combine two half cells and make it a working cell wherein E value is positive. So if I am writing like this, how do you identify the reactants? I don't think it's difficult. This is the reducing agent. I write this, and this accepting electrons, therefore I write this. And what do I get now? From this I am getting copper 0 state and zinc plus 2 state. Now, this particular reaction, galvanic cell, there is a conventional way of representing it. There is a conventional way. What is the conventional way I am referring to here? Instead of every time drawing the beaker, etc., what I will do is I will write like this. I am putting two symbols here. This is left hand electrode, and what we have here is a right hand electrode. Follow the minimum things here such that any problem in electrochemistry you should be able to solve it. Now always on the left electrode we refer to oxidation reaction only, or oxidation half reaction, left electrode. Therefore in the above zinc and copper example, I think zinc is losing electron, therefore it is undergoing oxidation. Zinc to zinc plus. Therefore we write down here oxidation half reaction. And what do we write in the right hand electrode? Reduction half reaction. Reduction half reaction. Let there be no confusion here. You can start off if you want right side reduction. Right side reduction. Try to remember. Some way sometimes will help you to remember things much better. So only thing is that you must identify which is the oxidation part, which is the reduction part. Let there be no confusion. We are talking about the actual half reaction now. In that process, zinc is losing electron, therefore this is the oxidation part of that. And copper plus 2 is accepting electron, therefore this is the reduction part of that. So what we do is left hand electrode, I am writing like this, try to follow. I will write down zinc, zinc plus 2, zinc plus 2. I am using a notation. This slant line indicates the phase boundary, phase, PHASE, phase boundary between zinc metal and zinc in the ionic state. Phase, that symbol used here. Now similarly, what do we have this side here? Copper plus 2, copper. This is the other half cell. I think this is undergoing reduction, this is undergoing oxidation. We have seen that quite good number of times. And in between we put two lines which indicates that bridge, contact point, remember that U-shape this thing here. This is bridge between the two half cells. Now, what was the E naught reduction potential for this volume? It is minus 0.76 volts. This data we have already given to you. What was the E naught RP value for this? This RP value is 0.34 volts. I think so, 0.34 volts. So both are reduction potentials. Ensure that before you take up the problem, clearly watch out whether the examiner is giving you reduction potential or oxidation potential. By convention, he must give you only reduction potential. In case if he is giving oxidation potential, you have to change that. Change from negative to positive or positive to negative sign depending upon the data. That will consider us if time permits today. So how do you find out the net EMF value? How do you find out the total potential value for the movement of electron? So what we do is, we will follow a simple rule position here, which I am writing above. The E of the cell, total cell, is equals to right hand electrode minus left hand electrode. Provided we are sticking on to this convention, half cells are reduction potentials. So this value is how much here? 0.34 minus, what is this value? Minus 0.76. 0.76. Therefore, what is the value you are getting here? About 1.1 volt or 1.1 or around that value. Is it a positive value? 100%. If it is a positive value, that means the reaction is spontaneous. At this stage, because we have started with thermodynamics in the introductory part, let me write down exact value. I am forgetting about this. So around, therefore you write down here approximately 1.1 volt. So in thermodynamics, we have a beautiful equation which says delta G naught is equals to minus NF E naught. E naught is what we are right now discussing. N refers to number of electrons in that particular half reaction. And F is of course Faraday. Now for a spontaneous process, what is the criteria? The delta G value must be negative. It will become negative once the E plus is positive. E is automatically positive means this is positive, N is positive, Faraday system positive, number of electrons always 1, 2, 3, 4, that's a positive number. So there is a negative sign after before that. Therefore my delta G will be negative for the above reaction. If the delta G is negative, what does it mean please? When do we get negative value? Provided my E value is positive. Therefore, if delta G is negative, that means that particular redox reaction or the movement of electron from reducing to oxidizing agent shall take place spontaneously. This is the fundamental aspect of the galvanic cell. You must bear that in mind. We'll take one more example now. The same example that I was talking some time back. What was the example we started today? Actually, this electrochemistry topic, a reaction between sodium and chlorine. Shall we write down again and try to find out the In similar, the convention also we try to repeat that. The reaction is, therefore, I require again data about the E naught for both of them. So E naught for sodium, E naught, see how I am writing here, Na plus Na. Does it look like reduction process Na plus Na? That value is minus 2.71. Minus 2.71 volt. Ensure you are taking it. I am repeating that point. If you commit mistake here, our calculation will go wrong. First steps in any subject, any topic must be taken very carefully. Now, I have combined it with chlorine. Is it not? For chlorine, the value is Cl2, E naught for Cl2, Cl minus. Whether right half or not, it doesn't make a difference here. And this particular value is plus 1.36, plus 1.36 volt. This is a necessary data. Without data, we cannot proceed. Of course, being a familiar case, we can predict the net EMF value must be positive. But instead of making statements in English language, if we assign a number for that assertion, that is always a soundproof argument in sciences. That is the importance of numbers in sciences. Now, if you take this case here, now what is the actual reaction please? Na getting converted to Na plus electron. If you remember from the overall reaction is Na plus half Cl2 giving rise to NaCl. This was the overall reaction we have talked some time back. Is sodium undergoing oxidation? Therefore, this is the oxidation of reaction. So again, try to follow. This is left hand electrode. This is right hand electrode. What type of reaction must indicate here? Where oxidation is taking place. Therefore, I will write down here what? Na, Na plus. This part of the reaction I must indicate here. And what type of reaction I must write here? Reduction. Right side reduction. Left side oxidation. So this reaction is chlorine Cl minus. Then what next please? You must check out what is the E naught Rp value here. E naught Rp value is 1.36 volt. And what is the E naught value for this reduction potential? Minus 2.71. Therefore, what is the net EMF value? Net EMF value is right electrode potential minus left side. Therefore, I will write above same thing. So for the sodium plus chlorine reaction, I can write down the E net is equals to E naught Rp right hand electrode minus E naught Rp left hand electrode. So what is the value for this right hand electrode? It is 1.36 minus, and what is this Rp value? Minus of 2.71. Therefore, this is equals to 1.36 plus 2.71. I think this is equal to a positive value. Now, what is the meaning of positive value? The reaction shall take place. And have you understood the galvanic cell representation as is conventionally done? Yes. If you have understood that, you will be able to fluently solve a numerical problem. Right now, I am taking only simple cases. Let me take a third illustration of how to use this. Now, one of the experiments normally we do in the lab is titration reaction involving potassium permanganate plus ferrous. What is the reaction? Let me write that. So that even if it is coming in a slightly different way, you must be able to handle that question slightly different way. What we do in the lab, I am writing first. What are we doing in the lab? I am taking MnO4 minus, and this is reacting with ferrous solution in presence of H plus to form Mn plus 2 and ferric solution, and of course some water. I am not balancing this reaction because my purpose is different here. I am taking a familiar example that we normally do at the lab level. and try to convert to our present situation of a spontaneous chemical reaction. You can make out here, before I go to galvanic cell argument, as a qualitative argument, this oxidation number over MnO4 minus is plus 7, this is plus 2. So manganese plus 7 is getting converted to plus 2. That means the oxidation number has decreased, so it's undergoing reduction. Therefore, it is an oxidizing agent. It is an oxidizing agent. Are you following my point, please? What about this fellow? Fe plus 2 is getting oxidized to Fe plus 3. Is it oxidation? Because there is increase in oxidation number. So it is a full-fledged, a very popular and familiar redox reaction that we normally carry at the lab level. And this reaction is taking place. Only thing is we must keep the chemicals in contact or act each other. So if you watch out here, how does my data appear in the tabular form, both as reduction half reactions? So for permanganate, they will write down MnO4 minus Mn plus 2. Does it look like reduction? Because there is decrease in oxidation number. Therefore, in the tabular form, we have E naught value. Some value they will suggest. I will refer to book and write down. Similarly, other reactions also reduction, because the data is coming only as reduction half reactions. So that will come as ferric to ferrous. Does it look like reduction? Yes, there is a decrease. Therefore, for that also E naught values. Both are coming as reduction potentials and reduction potentials. So I will give you the data now. For permanganate ion, the data is for that particular half reaction, KMnO4 minus. It is 1.5 approximately. 1.55 volts. 1.55 volts. That is the reduction potential for permanganate reduction reaction. For ferric to ferrous, that value is 0.77. Ferric to ferrous. This is 0.77 volt. Please copy them. For this reduction potential, this is 1.55. For the latter reduction, it is 0.77. Now, once we have the values, what next? We must correctly interpret and go for the galvanic representation for that. I am writing here, try to follow. What is the conventional galvanic representation? We have a left hand electrode and this is right hand electrode. Now, what type of reaction we write on the left hand electrode? Oxidation. Now, what is the original reaction which is undergoing oxidation here? Ferrous is getting oxidized to ferric. Is it not? So, as per the experiment I am talking here, as per the experiment, beautiful experiment, some of you might have done that already. So, this is oxidation half reaction and read down. From the overall reaction, if you remember, ferrous was getting oxidized. And which is getting reduced? Permanganate was getting reduced. So, this is reduction half. So, what should I write here? This is 1/2 of the reaction. And this is what? Mn plus 2 and MnO4 minus. So what is the E naught value for this reduction potential? It is 1.55 volt. And what is this please? 0.77 volt. In that case, try to follow what I am talking here. What is the net EMF value? Right minus left. This is the right side, the left side. So 1.55 minus 0.77, that is the E naught net. Is it not a positive value? Definitely. If it is a positive value, what does it mean? The corresponding delta G will be negative. If delta G naught value is negative, that means the reaction is spontaneous. That is, the reaction as written will take place. It's a beautiful reaction. If you remember, permanganate has a purple color, and if you're adding from burette to a beaker containing a conical flask containing ferrous is a light green color. Purple color is more conspicuous because of its color. As it comes in contact, the purple color vanishes quickly. That means my permanganate ion is getting converted to Mn plus 2. Permanganate has color. Mn plus 2 has no color. Very quickly it is getting converted to Mn plus 2. If it is getting M plus 2 means, that means the other reaction must be taking place spontaneously. What is the other reaction? Ferrous is getting oxidized. Beautiful reaction. So let them give any half reaction data. You must be able to correctly predict which is the oxidation reaction, which is the reduction reaction. And next, Bear in mind the data is coming in terms of reduction potentials only. Correctly what's called put on the conventional galvanic cell without confusion. Right side minus left side will give the net EMF value. If that is positive, delta H is negative. If delta H is negative, that is a spontaneous redox reaction. Hope the illustrations are clear for you. We shall be. Thank you very much.